So, yesterday I attempted a few Dynamical Systems tripos past paper questions, and I guess I wanted to, for my own sake, go through and reflect on, what I learned from each question, what the trick was, if there's anything in particular I want to remember for my revision. So, we'll start with the question from 2014. If it's going to work, because I've tried recording this already and it just broke. So, paper 4, section 2. So it's this question, and it's on the questions I attempted yesterday. They're all on kind of classification of stability and using the Lyapunov functions and Lassalle's invariance principle, and so on to, show, for example, asymptotic stability and the domain/basin of attraction stability, blah blah. Yeah, so this question says we have a dynamical system with a fixed point at the origin. You want to define the terms, so it's quite straightforward. I just drew a few pictures to help me remember what the definitions were, and after drawing the pictures, I then wrote out the definition. The Lyapunov function, I think. Yeah, this was fine. That's just book work, and now the Lyapunov's first theorem, which tells you that, if there exists a Lyapunov function, within a domain containing a neighborhood of 0, a fixed point, then the origin is Lyapunov stable. So, yeah, again with this proof, I think the best thing for me was just to remember this picture and to, from the picture explain what was happening, and then I think it's, quite straightforward from there. Lassalle's theorem, you just have to state that. I got a little bit confused with this, and I think I want to explain a bit more than I think I didn't explain very well in my previous video. So, essentially, it says that for the Lyapunov function, for a flow phi, first of all, it says that phi is bounded, and that the omega limit set, it exists, and it is going to be a subset of basically all of the values. Sorry, it's going to be fixed contours of the Lyapunov function v. And it's going to be all of the points that go to these fixed contours. Yep, so now onto the real meat of the question. We consider this system. Yeah, I'm going to start skimming through this because I don't want to, it's not a walkthrough, I just want to highlight key points. The key thing with this is to notice that this system is near Hamiltonian, so we're going to, I think the easiest way to do this is, just take away the y term from y dot and take away the x terms from x dot if there are any. In this case, there are not. And so, we're left with this system. And then, we just treat this as a Hamiltonian system, we write it as a Hamiltonian, and then we take account of that extra term that makes the system non-Hamiltonian. And it turns out that, quite conveniently, h dot is less than or equal to 0, which makes h a non-strict Lyapunov function for the flow phi. Yeah, so that only shows that the origin is Lyapunov stable. Now, we need to do Lassalle to show that this is the only possible fixed point. And so Lassalle would show you that, the existence of invariant sets lying within a subset, and it turns out that we find out y is equal to 0, so the invariant subset lies in the x-axis, and if we draw a little diagram here, the only time when h dot is less than 0, is, and we want h dot to be less than 0, or less than or equal to satisfy the definition of the Lyapunov function. For that to be true, we want to, choose, say, this circle that doesn't go through these 2 points, -1 and 1. So we choose, exactly that, and that satisfies the property, so we're done. This bit of the question was a bit interesting. It says, find the greatest value of y0 such that the Lyapunov function guarantees the trajectory through 0, y0 approaches the origin. Yeah, so I mean that's just from the boundary of the domain of stability and from the definition. So we're looking for, the biggest contour of the Lyapunov function that doesn't enclose x is equal to -1 and +1. And so we just evaluate the function as those 2 points, find out which has the smaller constant value of the Lyapunov function. And it turns out they're both the same, they're 112, and so we plug that in and we solve for y, and that's done. For part B, yeah, so this part I struggled with, I shouldn't have in hindsight, and so that's why I want to highlight this. Yeah, the question actually suggests using this Lyapunov function because they're saying in the region blah, so that better be the Lyapunov function, so that's what you choose. You use polars to show that this thing is not 0 except for at the origin. So it took me a while to figure that one out. And then you just do some differentiation, being careful to, not make any algebraic mistakes. And when I got to this point, I was like, what? It turns out it's not that hard. My approach was to just say, pretend we're in some circle of radius A. We don't know what A is yet, but we want to choose A such that v dot is less than 0 within this disk. Then, we just plug in A into all of this stuff. And it gives us, the inequality A is less than 1/3. So, well, clearly the disk of radius 1/4, not a disk, sorry. Clearly this Lyapunov function, the region where it's less than 1/4 is a subset of the region where it's less than 1/3. And so, yeah, we've answered the question. Next question, 2015, paper 1. Yeah, so it's this question. Define a Lyapunov function, easy. Then we consider this dynamical system, and we want to prove that the origin is asymptotically stable, and the domain of attraction of the origin includes this. So yeah, reading ahead in the question is quite useful here because it tells you what the Lyapunov function to use. Oh, where is it gone? Yeah. No, not that. Here. So yeah, it tells you basically this is the Lyapunov function you want to use. So you use that, you get this, and we're going to argue that, if we were to do this in polars, then, this first bit is order of r squared, and this is order of r to the 4. So, sufficiently near v dot will be less than 0 because this order of r squared term is strictly negative. Yes. So, this bit is also very strange. Show that the domain of attraction of the origin, blah, 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 determine the maximum possible value of R1. So, yeah, you parameterize the thing, and you find that, for this parameterization, v dot is, we want it to be less than 0, and then we have r is less than root 2 plus sine 2 theta, where theta is between 0 and 2 pi, and so if we find the supremum and the infimum of that, then we get R1 and R2 respectively. Sorry, the infimum supremum, we get R1 and R2 respectively. Yeah. So part B, show that there's a periodic solution. So this actually uses some stuff that I haven't gone through in the previous video. It uses the Poincaré-Benedictson theorem, which tells you essentially that if you have an annulus, say, centered around the origin that you cannot leave. So if a trajectory ends up in here, then it's going to get trapped in here for a time. If you have that, and you also have, I think, something about compactness, and the annulus contains no fixed points, then you must have at least one periodic orbit, and to show that there is exactly one, i.e. there can't be, more than one, you show that, I think, nabla dot f phi is less than 0 within the annulus. I'll check that later, but I believe that's true. So that's the idea. We're going to have to remember to import and formulate this for r dot and this for theta dot. So for r dot, we're just doing this to find out what that annulus is. We're going to get something in terms of theta, and because this half sine 2 theta term, is variable, it varies with theta, we can we can bound r dot above and below in terms of r, and so we can find out when these two things are 0 and define the annulus. Now we want to check whether the annulus contains any FPs so that we can use the corollary of so that we can use Poincaré-Benedictson. So just show that this thing is not equal to 0 for theta. That's done. And to show uniqueness, as I said, here we have chosen, so I did make a slight blunder. This should be phi f. In this case, we're just going to choose phi is equal to 1. So that's fine. Equivalently we choose phi is equal to -1, whatever we want. And we're just going to show that this is strictly less than 0 in the annulus, which by Dirac criterion, which is a corollary of, I think, Dirac's theorem, which is a negative test for POs, there are no POs not encircling the whole of the annulus, which means, if we did some integration, well, you can just try and see this. If there are multiple POs encircling the whole, then you would consider the integral over this shaded region between the two POs, and there would be some contradiction. So there's exactly one PO. And lastly, I didn't quite finish this question because I was tired and went to sleep. 2020. What is this paper on S2? Where has it gone? Apologies. So I think it's this question. Yes. So this is more, I guess, bifurcation-y. I don't know why at the beginning of this video I said this was all stability. It's not. Sorry for the lie. So I guess for this one it was just sketching. The important thing was not to get overwhelmed with, there's 3 cases you have to sketch. Oh no. I think it is quite obvious after you sketch the first case that, when you move this A, it's just going to give you the other 2 cases quite easily. And you can just do that by continuity arguments and by considering, when you have a pitchfork bifurcation, whatever the stability is before the pitchfork is going to be the stability of the outer 2 prongs of the fork, I guess. Yes, so I'll have to go through this again and then actually it's fine. So to confirm the types of bifurcation, we expand the system to leading order near each of the bifurcations, and to do that we recenter the system to the bifurcation point first, and then we show that it's in the right form. For pitchfork, you will now get something x cubed, something x, plus or minus something x. And for a transcritical, you will get something x minus something x squared. I think it's plus or minus actually. And I can't quite remember what it was for saddle node. Oh well, it would just make sense if it were something mu minus x squared, because then you would get x is equal to plus or minus mu. So I guess it would be constant term and an x squared term, as opposed to in the transcritical where it's linear term and quadratic term. And I guess that's the end of the video. Just wanted to make a quick video to, recap what I'd learned, mostly just for my own purposes, but if anyone finds this helpful, then good side effect. Bye.